Welcome to Tutorial 8, where we're going to be discussing correlation and regression. Correlation and regression are important and flexible techniques used to analyze interval-level relationships. Pearson's correlation coefficient measures the strength and direction of the relationship between two interval-level variables. It ranges from -1, perfectly negative association, to 1, perfectly positive association, with 0 indicating no relationship. Regression analysis produces the regression coefficient that estimates the effect of an independent variable on a dependent variable. Regression also produces the R-square, which is the coefficient of determination. This indicates how the independent variable, or variables, explain the dependent variable. The dependent variable is measured at the interval level, but the independent variable can be in any form, nominal, ordinal, or interval. In this tutorial, we will learn to perform correlation analysis and also how to run bivariate regression and multiple regression. So let us begin. Let us open the states dataset. And remember that we are going to be using do files in running the commands, just like we did in the last tutorial. So let's open the tutorial 8 do file. Suppose that we are interested in the gender composition of state legislatures. We can run the command sum wum-leg. And we find that state legislatures range from 8.8% female to 37.8% female. Why is there such a variation in this variable? So we begin to formulate an explanation. Do states with lower percentages of college graduates have lower percentages of women legislators than states with more college-educated residents? Or do states with higher percentages of residents who are Christian adherents, for example, have lower percentages of female lawmakers? Let us use the correlate command, or COR for short. And we try to correlate Christad, which are the Christian adherents, college graduates, and wum-leg, the variable we saw before. And we see that Stata produces a table called a correlation matrix, which shows the correlation of each variable with each of the other variables. From this table, we can deduce that the percentage of Christian adherents goes up, the percentage of female legislators goes down. We also find that as the percentage of college graduates go up, so does the percentage of female legislators. And we can see that both relationships are fairly strong. Now remember though, correlation analysis is agnostic to the question of which variable is the cause and which variable is the effect. So, does an increase in the percentage of college graduates increase the percentage of female in legislatures, or do increasing percentages of women in legislatures somehow cause states to have higher percentages of college graduates? We need to think about that. Either way, however, the correlation analysis reports the same measure of association, a Pearson R of 0.58. What we can do then is turn to regression, which is a more powerful analysis tool than correlation. Let us run regress wum-leg, which is the dependent variable, followed by Christad, which is the independent variable, Christian adherents. And you can also use rig instead of regress. In the output window, we see our regression results. What this is telling us is that the constant, which is the estimated value of y when x equals 0, is 37.93. The coefficient for the state's population who are Christian adherents is -30. Then the regression equation for estimating the effect of Christian adherents on women legislatures is the percentage of state legislatures who are women equals 37.93 minus 0.30 times Christad, which are the Christian adherents variable. So, estimating for a state with 50% Christian adherents would be 23% of that state would be female legislators. Focus on the negative 0.3 or 0.30 regression coefficient. What this is telling us is that for each 1 unit increase in the percentage of Christian adherents, there is a 0.3 unit decrease in the percentage of female legislators. Now suppose for a minute that this data comes from a random sample, and we want to test our hypothesis that the more Christian adherents a state has, the less likely are women in the legislation position. We will need to examine the 2 columns in the bottom table. The column labeled T, which reports T ratios, and the column labeled P greater than T, which reports the P values. To safely reject a null hypothesis, you should look for T ratios with a magnitude of 2 or greater. According to our results, the negative 3.45 T ratio passes this threshold. The p-value tells us the probability of obtaining the results if the null hypothesis is correct. If the p-value is greater than 0.05, then the observed results would occur too frequently by chance, and you must not reject the null hypothesis. By contrast, if the p-value is equal or less than 0.05, then the null hypothesis represents an unlikely occurrence and may be rejected. So here, the p-value is less than 0.05, so we reject the null hypothesis. Let us stop for a moment and consider the R-squared and the adjusted R-squared. Remember that the R-squared provides an estimate of the true value of the R-squared in the population, and it is a measure of how well a regression line approximates real data points. An R-squared of 1.0, 100%, indicates a perfect fit. Adjusted R-square is often about the same, but always less than the plain R-squared. It is a modification of the R-square that adjusts for the number of terms in a model. R-square always increases when a new term is added to a model, but the adjusted R-square corrects for an upward bias and increases only if the new term improves the model more than would be expected by chance. Let us look at the adjusted R-square, which is equal to 0.182. What this is telling us is that all of the variation in the variable womb-leg between states, 18.2% of the variation, is explained by the Christian adherence variable, and the rest of the variation, which amounts to 81.8%, remains unexplained. Okay, let us now run a similar regression, but this time with the college independent variable. What this is telling us is that a regression coefficient, 0.94, that for each percentage point increase in college, there is an average increase of 0.94 of percentage point in the percentage of female legislators. Again, increase the percentage of college graduates by 1, and the percentage of women legislators goes up by almost 1 on average. The T ratio of 4.93 and the p-value of 0 tells us that we can reject the null hypothesis. Finally, the adjusted R-square is telling us that about 32% of the variation is explained by our independent variable. And for a bivariate regression, that is a good percentage. Now, for graphing this relationship, we will use a scatter plot, and for that you can use the two-way command. We look at the following command: two-way scatter womb-leg college, lfit womb-leg college, legend off, which you can use to obtain from the drop-down window as well. And this will produce for us the graph that we want. And we can do some editing using the graph editor. And we have a new enhanced graph showing the percentage of women legislators by college graduates. Now we will take our regressions a notch up and move from bivariate regressions to multivariate regressions. Suppose you want to investigate factors causally related to motor vehicle deaths in the States, and we could base our factors on assumptions. One factor could be how densely populated the states are. And we hypothesize that as density goes up, fatalities goes down. The second factor could be demographic. So as the proportion of young people goes up, fatalities go up too. We first begin with the correlate command. So we correlate car fatal, density, and the population variable. And we find indeed a strong negative correlation with density variable at negative 0.57 and a moderately strong positive correlation with the population variable at 0.39. Now, before running our multivariate regressions, let's run a simple regression. We regress car fatal density. And the output shows that we have a coefficient of negative 0.012, indicating for our formula that as density increases by one person at a time, fatalities decrease by 0.01 of a fatality per 100,000 of a population. The t-ratio of negative 4.85 and the p-value of 0 tells us that we can safely reject the null hypothesis. Finally, the R-squared is telling us that the variation in the fatality rates can be 32% explained by the population density. Next, let us run another simple regression, and we regress car fatal and the age variable population underscore 18 underscore 24. The output shows that we have a coefficient of 2.7, indicating for our formula that each percentage point increase in the population variable, there is a 2.73 unit increase in the motor vehicle fatality rate. The t-ratio of 2.92 and the p-value of 0.005 tell us that we can safely reject the null hypothesis. Finally, the R-square is telling us that the variation in the fatality rates can be 13% explained by the population age. Now, these two factors obviously have a clear impact on the car fatality variable. But what if we want a model that looks at the two independent variables together? This is where multivariate regression comes in. Multivariate regression is designed to estimate the partial effect of an independent variable on a dependent variable, controlling for the effects of other independent variables. We run another regression, which looks at two independent variables, the density and the population age. As you can see, the coefficient column provides the information we need to isolate the partial effect of each independent variable on the dependent variable. And we can come up with a multiple regression equation. It looks like this. Motor vehicle fatalities per 100,000 population equals 9.13 plus 1.04 times the percentage of those between the ages of 18 to 24 minus 0.01 times the population per square mile. The coefficient of the population, 18 to 24 variable, tells us the effect of this variable on the car fatality controlling for density. And the effect of the population between 18 and 24 variables in the multiple regression has dropped from 2.73 units in the bivariate regression to 1 in the multiple regression. And this is not significant anymore. Density, on the other hand, has retained its predictive power and remains significant. So this is telling us that the population variable is a spurious artifact of difference between states in the population density. Remember, a spurious correlation occurs when two variables have no direct causal connection, yet by mistake it is inferred that they do. Finally, we know from our adjusted R-square that with this model we can account for about 32% of the variation in motor vehicle death rates, and it is density that does the lion's share of the explanatory work. This brings us to the end of tutorial 8. Let us now move on to tutorial 9, where we will cover dummy variables and logistic regressions.